So we cover the topic of continuity or continuity in section 1.3, and I'm going to do it kind of informally rather than formally specifically because, this is brief calculus and not traditional calculus for math majors. So I just want to get the concept down so we understand what we mean when we say a function is continuous at a point or not continuous at a point, but not get too deep into the weeds, but deep enough so that we're doing something equivalent to what they do in a Math 220 calculus class, just with maybe words that aren't as mathematically elegant, but still accurate. So we're covering the concept of continuity at a specific value or at specific values of x in this section. And I'll say informally, a function is not continuous, or we can say the function is discontinuous at a value of x. So I'm going to flip-flop real frequently between saying a function is not continuous at some value of x, and that x is going to have a number. So I'm going to flip-flop all the time between saying a function is not continuous or saying a function is discontinuous at some value of x. So I'm going to use discontinuous and not continuous interchangeably, and I won't even realize when I'm saying one or the other. So the words have the same meaning for us. Anyways, we say a function is not continuous or discontinuous at some value of x, and that a just stands for some generic number, if one of three things happens at the graph above x equals a or below x equals a on the x-axis, above or below. Either there is a hole in the graph at x equal to a and the function is not defined at that value of x. There's a hole in the graph at x equal to a, but the function is defined at that value of x, meaning f of that value does not exist. If there's a jump in the graph at that value of x, or if there's a vertical asymptote at that value of x. And let me show you what I mean pictorially. This is all pictorial to start. So I have a picture of a function, and when I look at the graph, there's a hole in the graph at the point x equal to 2, y equal to -1. So I would say this function is not continuous at x equal to 2 because there's a hole. If there's a hole in the graph then at a point, then the function is not continuous at that value, or it's discontinuous at x equal to 2. So it would be proper to say that this graph is discontinuous, or it's not continuous at x equal to 2. So there are two different things that can happen to make a function discontinuous at a hole. Either there's a hole in the graph and the function is undefined, or there's a hole in the graph and the function is defined. Here, if I look above and below this open circle, there is no corresponding closed circle, so the function isn't defined at this value of x equal to 2, so this is the top reason. There's a hole in the graph at x equal to 2, makes it discontinuous there, and the function is undefined there because there's no point with a solid circle at x equal to 2. So this is my first example of a function being discontinuous or not continuous at a value for x. In this case, the value where this function is not continuous is at x equal to 2 because there's a hole, and it's kind of an unplugged hole in some sense because there isn't a corresponding value that's defined for x equal to 2 on this function. If I just take that same graph and add a point, this function is still not continuous at x equal to 2 because there's a hole at x equal to 2. But unlike the last function, this function is actually defined at x equal to 2. So both the graphs that I've shown have not been continuous at x equal to 2 because there's been a hole there. There's two kinds of holes. There's holes where the function isn't defined, and there's holes where the function is defined at that value of x. This one, the function is defined at x equal to 2 because there's a point on the graph of the function that has an x coordinate of 2 that's marked with a solid circle. This is what case 2 looks like. Case 1, there's a hole in the graph, but not a corresponding plug somewhere above or below that point. Case 2, there's a hole in the graph, but there's a plug for it in some sense above or below that point. So this is an example of case 2. There's a hole in the graph, but the function is defined. That point is taken away. There's a hole in the graph and the function is not defined. This is what a jump looks like. Problem 3. At x equal to 4, I call this a jump. Actually, I didn't call it a jump. A student that I was tutoring, must be 5-6 years ago, came up with the word jump, and I stole it from her. So here, there's a break in the graph. There's a gap between the point 47 and the point 44. They're not connected by a hole. There's a hole on one end and a solid circle on the other. This is what I would call a jump. This function, I'd say it's not continuous, or it's discontinuous at x equal to 4 because there's a jump. The graph is disconnected. There's a top half and a bottom half that don't connect up at x equal to 4. And the last thing that can happen is I can get a vertical asymptote. And I don't know how well this vertical asymptote is showing up, but this dashed line that I drew goes through x equal to 5. There's a left half to this graph and a right half to this graph. And at x equal to 5, there's a vertical asymptote. I'd say this function is not continuous, or equivalently, it's discontinuous at x equal to 5. And the informal reason is because there's a vertical asymptote. This is what they teach in a regular calculus class. And I don't think I want to get so deeply into it. But in a regular calculus class, they would ask you, these are the formal reasons. Which one of these reasons is the function not defined? And I just think this is a bit much, and it doesn't really add anything to the understanding of continuity. And we don't need continuity as we get out of chapter 1 into chapters 2, 3, 4, and 5. So I'm just gonna pretend that you read this, but it's not important. But if somebody else is using my material, then the formal reason is there, and they can teach it to their students, but it's not important. I think just having the concept of holes that are plugged, holes that are unplugged, jumps and vertical asymptotes are enough. If a function doesn't have a hole, a jump, or a vertical asymptote, if the graph of a function doesn't have a hole, like this doesn't have a hole, it doesn't have a jump, it doesn't have a vertical asymptote, we say that this function is continuous everywhere. It doesn't have any values of x where it's discontinuous or where it's not continuous. So if there's no hole, no jump, no vertical asymptote, the graph of the function is continuous everywhere. So now we need to deal with some algebra. How do I find algebraically where the function is not continuous, and how do I decide whether it's a hole, a jump, or an asymptote? And if it's an unplugged hole or not. So let me show you. I should have boned up on my calculator skills like I told myself to, but I didn't. So when I'm given a fraction, any value that makes the denominator of the fraction equal to 0 will either make a hole or will make a vertical asymptote. And I'll have to do algebra to figure out which. So to figure out where this graph has either a hole or a vertical asymptote, I set the denominator equal to 0 and solve for x. So this graph, it's not going to be continuous at x equal to 1. I have to know whether there's a hole or a vertical asymptote. If I graph this on my calculator, I think I can get it to show what I need it to show if I zoom decimal. I'm not so talented with my calculator, as a lot of students are much better than me. If I graphed this with my standard window, I'm not going to see a vertical asymptote, but I'm also not going to see a hole. I claim that there's actually a hole around x equal to 1, and I think if I hit zoom in decimal, I think it'll make me see the hole. Well, if I make the window bigger, let me make the window way bigger. How about, I'll start off with negative 30 to 30 for the x's, negative 30 to 30 for the y's, and then tried zoom decimal, I'm trying to do something that I really don't know how to do on the fly, which is just stupid. Now if I do zoom decimal, I still can't see it. Unfortunately, I'm not bright enough to know how to do this. I don't know if I can go zoom out, and hit enter. I don't know what that's going to do. Did something, but it didn't show me the hole that I want to see. Let me do zoom out again. Zoom out. And then we try one last time. I don't know that I can do this. And now to try zoom decimal. Yeah, forget it. There's a hole there. And I can at least tell there's not an asymptote. When I do zoom standard, I see there's no asymptote above 1 on the x-axis, which means there's a hole there that I don't know how to make my calculator show. How can I tell without a calculator, without a graph, that there's a hole as opposed to an asymptote? Because when denominators of fractions are equal to 0, they either produce holes or they produce asymptotes. They produce holes when you can factor the numerator and cancel out the denominator. So in this particular problem, if I factored the numerator, that numerator factoring will cancel out the denominator, and that produces a hole. So, and the function is not defined at 1. In order to get the example where the function is defined, I have to define a function as a piecewise function. No individual fraction by itself can be defined at the value that makes the denominator 0. So for this particular problem, any value that makes the denominator equal to 0 is a value of x where the function isn't continuous. There's a hole if I can factor and cancel out the denominator. There's a vertical asymptote if I can't factor and cancel out the denominator, and that's what I tried to write up here. There's a hole if you can factor and cancel out the denominator with the numerator. There's a vertical asymptote if you can't cancel out that factor. And this is, maybe I even sloughed off a little bit on my formality. There's a hole if the factor that made the point of discontinuity cancels out. There's a vertical asymptote if the factor that makes the point of discontinuity doesn't cancel out. And that's going to show up on this next example. For this, no it won't. Won't show up at all in this next example, and that's right okay by me. So where is this graph going to have breaks in it? A function, the graph of a fraction isn't continuous. It has either a hole or a vertical asymptote at values that make the denominator equal to 0. So just like in the last problem, I tried to figure out where the denominator was 0 to figure out where the graph wasn't continuous. That's what I'm going to do here. Algebraically, it's a little bit harder. This I have to factor. This factors into x plus 7 times x minus 2. X plus 7. And then once I have it factored into x plus 7 times x minus 2, to get the values of x where the graph it's not continuous, I set the x plus 7 equal to 0, and I minus 7 from both sides, and get x equal to minus 7. I take the x minus 2, set it equal to 0, and add 2 to both sides. This function, any value that makes the denominator of a fraction equal to 0, is a value where that function is not continuous. So this function is not continuous at -7 and +2. Now, I have to decide if there's asymptotes or holes. They're holes when I factor everything that can be factored. If I could cancel out one of the factors, then I get a hole. If I can't cancel out the factor, then I get a vertical asymptote. So in this problem, I can't cancel the x plus 7, I can't cancel the x minus 2. So there's going to be vertical asymptotes at x equal to -7 and x equal to 2. So this function is not continuous at -7 and 2. And for the reason there's going to be vertical asymptotes as opposed to holes, these I can show kind of. So if I graph the function y equals 6 divided by parentheses x squared plus 5x minus 14. And I think zoom standard should be enough. We're going to see over here, that's at x equal -7. There's a vertical asymptote. If I count it over there, that'd be -7. And that there, at x equal 1, 2, there's a vertical asymptote. You can kind of see the vertical asymptotes. My calculator doesn't really draw them in, but I know that they're there. I can see the breaks, and those breaks certainly don't look like holes. Those are vertical asymptotes. Now, piecewise functions. The only way I'm going to get a jump is if there's a piecewise function. And when I'm dealing with piecewise functions, I'm doing some stuff off screen right now, trying to remember what I've forgotten that I told myself before I recorded this video to remember. And I can't remember. Let me pause and do a part 2. It might make this spill over into a part 3, but I don't want to jump into doing the piecewise function without being able to show you it on my calculator, and I couldn't remember off screen. So I'm going to move into a part 2, and I'll pick up with this problem in part 2.